Okay, in this video we want to talk about how to work with bounding box information in Vex. And this is something we've already seen being used by the attribute adjust node. So for example, the attribute adjust color node, as you know, can use the bounding box as a reference for the color ramp. And in this case, let's say we use Y as the element, and this would use the bounding box of the object in any direction and read from the ramp based on that. But the question is, how can we use this tool inside of Vex? And this is what we want to look at in this video. This can be really helpful for all kinds of things. Actually, when we come back to one of the very first examples we looked at, then remember we built this cartoon tree. And this cartoon tree, we solved the problem of making it to a cone by finding all the points on the top by using a group. And this group found everything on the top, and it was specifically not a primitive but a point group, and we then used the transform to scale this down, just this group, there you go, and we have had a cone. And this was cool because we could change the column number procedurally and it would still work. Now there's one problem though, and actually a student pointed this out. What if this tube is actually higher than my bounding box? I mean, I could theoretically make this, so tall that it will always, fit this. But that's a bit of a dangerous way of doing this because, for example, what do we do when the tube A is much higher than that and would still not kind of catch the points at the top? Or another thing could be that we move this thing to the side and then of course our group will not catch the points at the top. Now this is something, if I would run into this problem in production, I would actually solve with Vex, because I can find the points not based on any position in space, but on the position relative to the bounding box of the object itself. So as long as I can be sure that there are points at the top, so to say, and they're not, evenly distributed, because then, I'm lost anyway, I can actually find those points by calculating their position relative to the bounding box. And the bounding box, of course, is something we can actually visualize by using a bound node. There it is. And I basically just find the top points in that bounding box. So for this, there is actually the command Getbbox for get bounding box. And as you can see, there are multiple ways of working with this. One thing I very often use actually is the get bounding box center. So I could always find in Vex the center of an object. This is something we will use later. But for now, we can use the bounding box. Actually, let's look into the help to get the minimum and the maximum, but this is a bit more complicated because it uses so-called pointers, and this is here with an end sign. And what that means is that instead of using this as an input, it takes this as an output. Now is a good time to actually show you what that means. We have what this gives back is, and actually that's something that help gave us. This actually gives back a vector. So I can create a vector minimum and a vector maximum. Again, the names don't actually really matter. And as you can see here, I don't actually fill them with something. I just create them. And then I can read out the bounding box of the current geometry. So the first one is, as usual, 0. And then I give this min and max. And this is interesting, not as an input, but actually as an output, because what just happened is, as you can see, we didn't fill the result of the Getbbox into a variable, but we gave two variables that we already have. And this is again called a pointer. And here, by the way, the data type that comes back of this is void, which means there's nothing that comes back from it, but instead it writes into those two vectors. Why is it doing that? Because this function gives back two vectors, and a function in Vex cannot give back two things. So they found this solution, which is again marked by those end signs. And that says it will write into those vectors, which is special. So to prove that this actually did something, let's show what min gives us and what max gives us by putting it into actual attributes. And here you can see something comes out of it. And this is what happened here. This function wrote into those empty variables, and what it gives us is actually the minimum and the maximum values for x, y, z. What does that mean? In min now is the smallest number in x that any of the points of this geometry has. Then the minimum one is the smallest number in y, which would be those points here. And min z is the smallest z numbers. And the same is true for max. It gives us the maximum for x, so the highest number that any point has in x. Then the highest point that any point has in y, and here you should think about what we can do with that, and the highest number that we have in our geometry for z. Usually though, you only want minimum or maximum, you don't want both. And this is why I usually don't work like this, because it's, you know, too much work, basically. What I usually do is this. If I need the max in this case actually, because I want the highest points, I do a vector max, and then I use the helper function that has this separated in max and min. So there are two functions that already do this for me by splitting it up in either max or min. And this is much simpler because it only has one input, and that is the geometry input, which of course in this case is 0. So in other words, in max.y now is a number that defines the highest number this geometry has. And this, of course, can help us because we can now, by this, with the help of this, find all the points that are at the top. Because, you know, we could even say this. If the current position y element is the same as the maximum y element, so in other words, is the current position the highest in the geometry, then, I don't know, turn this point red. And this actually works, as you can see here. But I usually don't do this because it's kind of dangerous, because if one of the points is just, you know, slightly lower, then we will not catch it. So what I usually do is, if the current position in y is higher than the maximum multiplied by a certain number, for example, 0.95 or 99. So basically there's a 1% wiggle room where the points will be found. So if I try to show this, let me grab a couple of points and move them down slightly, which of course I would usually never do, but this time I do it. So like this. And those will be catched as well because they're in this 1% margin of error that this defines. Because otherwise, let me quickly show you what otherwise would happen. It would not match with the highest number, and those points would not be found. Which might be exactly what you want, so this is totally fine, but as a tip, give it a little bit of a wiggle room. Okay, and actually we could show this even further by increasing the rows, and here you can see we can actually increase that even, and now we can see it even takes the second line with it. And the cool thing about this is now, it doesn't matter where this is in space, it will always be red. Of course, if I rotate that, then it will change, but that's the exact idea. It will always find the top, so to say. But the position doesn't matter, and also actually the height doesn't completely matter, but it does matter in one way, and that is that the margin of error will change in a case like that, of course. But if I have my original case where I can assume that I have something like this, then it will work. So what can I do with this now? To finish this, I can call this now with an attribute top, and then transform all the points that have the top attribute set to 1, or actually I can do it like this. And as you can see, this works, and the only thing now I have to do actually is to do it relative to the center point. There you go. And now, okay, it scales to the center of the geometry, fair enough. I think, what could I do here? But you can see this way it works, and I can even move that thing around in space, and it will always do its thing, even when I change the height. So as you can see, this is why I didn't show you that in the beginning, because it's way more complicated, but just have a look at how helpful the bounding box can be. Oh, right, and before I forget, I actually set an attribute here and then used that as a group. Some of you might know there's actually potentially a better way of doing this, which I personally don't like to do for a reason I can't explain. And that is, you can actually create groups on the fly by simply call your attribute group and then lower dash and whatever you want to. Because then when you look here, you actually created a group with that name. And this is maybe a bit easier than doing this, because then you can literally just choose it from this drop down here, because you just not only create an attribute, you basically created a group. Yeah, okay, back to the video. Now, we will use this more later on, but one last thing when we talk about bounding boxes, and that is relative bounding boxes. And we could have actually used that here as well, but I wanted to start a bit simpler. But for now, let's have a look at another example we've already seen, and that is our mountain or landscape here that we colorized with a fit function. So let's quickly do this. And we drive this by the position in Y. And of course, it doesn't fully work because when we turn this into a color ramp, we can see, okay, down here is water, green grass, and some snowy mountaintops. It doesn't fully work, of course, because the Y is different to 0 and 1, so it repeats itself. So we could remap this height with a fit function and define our own range. So let's say -1 and 2, I have no idea, I'm just guessing here, and say, okay, this should then be remapped to our normalized 0 to 1. Yeah, 1.5 maybe, something like that, I'm guessing here. Yeah. So by I can guess that it's something like that. And as you can see, this actually works. But of course, it has one big flaw, and that is, as soon as I change the height of this thing, it doesn't work anymore. So let's increase the strength of our mountain, and you can see that it doesn't stick to it. And the reason is, of course, it's an absolute number. What if we would use, instead of an absolute number, use a relative number? And this is exactly where the next function comes in, the Relbbox, so the relative bbox. And what that means is you can calculate where the current point is relative to the bounding box. So you have a geometry and a position, and what comes back is a vector for x, y, and z. And let's quickly do this to analyze this. And I put this into the vector Relbbox and make this visible maybe in form of an attribute, of course. There you go. And let's now choose a point where we can see what his relative bbox numbers are. So I choose one on the top and only show this one. And you can see the relative bbox in Y is 0.7, which actually surprises me because I thought it's a high one. Let's pick another one. And you can see here, it's 0.96. So let's see if I lower this whole thing and now go back. And as you can see, the relative bbox for Y is still 0.96 because this now gives me, the relative bbox, the position of this point, not relative to space, but relative to this bounding box here. So if it's at the top, it's 1 for Y. If it's at the bottom, it's 0 for Y. If it's on this side for Z, then it's 1 because Z is positive. My head is in the way. Have a look. So Z is positive. So this point here will have a 1 for the Z element, and this point here will have a 0 for the Z element for relative bbox. And for X, it's the same. This here will be have 0.5 for X. This one will have a 0, and this one will have a 1 for X. And this is why we have three different, so we have a vector, so three different elements, because it will always give me the position relative to the X, Y, and Z of the bounding box. So in this case, that means we need the Relbbox Y, which is already normalized. So we don't even need to do our height thingy here. We can use the relative bbox of the height directly, which is the Y element. And again, which means the lowest point will be 0 and the highest point will be 1. And when we put this into a ramp, then it will, if we adjust it one last time, then it will always be correct. So if I change the height now, you can see it sticks to it, even if I go really low until it breaks, of course, which also means I can actually move that thing around in space up and down and sideways without changing the result, because of course the bounding box is not changing, just the position of the whole thing in space. Okay, so as you can see, working with bounding boxes is a really helpful thing. Not the easiest in the world, but if you get used to it, this is a very powerful thing that can solve a lot of problems for you that would be, in my opinion, otherwise, as far as I know at least, not be solvable. Okay, so this was relative Bbox and the Getbbox functions. So I hope this is helpful. Thanks very much and see you later. Cheers.